Some of the most popular recent algorithms for relation extraction are semi-supervised or unsupervised algorithms. Let's look at them. What happens if you don't have a large training set, but what you have instead are maybe just a couple of seed examples, or maybe you have a couple of high precision patterns? Can you use those seeds to do something useful? In the seed-based or bootstrapping approaches to relation extraction, we use the seeds to directly learn how to populate a relation. The intuition of the seed-based method from Hurst 1992 is to gather a set of seed pairs that have a relation and then iterate the following. We find sentences with these pairs, we look at the context between or around the pairs, look at the words before or after or in the relation itself, and we generalize this context to create some patterns. We use the patterns to search for more pairs. If we're on the web, we're searching the web. If we're in a large corpus, we look in this corpus. We find more pairs, and now we just iterate. We take these pairs, we find sentences that have them, we find more patterns, we generalize the patterns, and so on in this iterative loop. So suppose we're looking for where famous authors are buried, and we know that Mark Twain is buried in Elmira, New York. So we might start with that single seed tuple. We might grep or Google on the web for all environments of that seed tuple. So we might find sentences like these. Mark Twain is buried in Elmira. The grave of Mark Twain is in Elmira. Elmira is Mark Twain's final resting place. And then we take out the actual entities and create little variables. So we learn X is buried in Y is a pattern, or the grave of X is in Y is a pattern, or Y is X's final resting place. So we learn these kind of patterns. We take those patterns, grep for more tuples, and then we iterate. And this approach was first applied by Sergey Brin in 1998, who looked at the task of extracting author-book pairs. So we might have authors like Isaac Asimov in The Robots of Dawn or William Shakespeare in The Comedy of Errors. So first, we might find instances. So imagine for Comedy of Errors, we happen to find these 4 instances. The Comedy of Errors by William Shakespeare was, the Comedy of Errors by William Shakespeare is, the Comedy of Errors, one of William Shakespeare's earliest attempts, and so on. And now we extract patterns from these, and one way to do this is to group all these patterns by what's in the middle. So these two both have comma by in the middle. And now we take the longest common prefix or suffix of the before and after parts. So both of these have nothing before, and both of these has a comma after. So we'll extract a pattern saying we have an X followed by comma by, and then a Y followed by a comma. Or in these two patterns, they both have comma one of in the middle, and they both have nothing before, and they both have an apostrophe S afterwards. So we can extract the pattern X, and then comma one of, and then Y, and then apostrophe S. And again, we iterate now that we've got some new patterns, and we find new seeds that match that pattern, and we continually iterate. The Brin approach was improved in the snowball algorithm, a similar iterative algorithm, and similar kinds of grouped instances to extract patterns. And the extra intuition of snowball was the requirement that X and Y be named entities. So in the DPRE algorithm, X and Y could be any string. Now we're going to add the intuition that each of those things have to be a particular named entity. That's going to help us because we know that we have a relation between organization and location. And again, we extract words in between or before or after the two patterns. And the snowball algorithm also computed a confidence value for each pattern. So that's kind of a new intuition. Another semi-supervised algorithm extends both of these ideas by combining the bootstrapping algorithms that we saw with the seed-based methods with the supervised learning algorithms we saw in the previous lecture. So instead of 5 seeds in a distance supervision algorithm, we take a large database and we get a huge number of seed examples. Now from those huge number of seeds, we have a big database. We could have hundreds of thousands of examples. We create lots and lots of features. And now, instead of iterating, we simply take all of those features and build a big supervised classifier supervised by all these facts that we know are true in our large database. So, like supervised classification, in distance supervision, we're learning a classifier with lots of features that's supervised by the detailed hand-created knowledge in some database, but we're not having to do the complex iteratively expanding of patterns that we saw in the seed-based method. But like unsupervised classification, distance supervision lets you use lots and lots of unlabeled data, and it's not sensitive to the genre issues that you might have in supervised classification. So let's see how it works. For each relation, let's say we're trying to extract the born-in relation. We go through each tuple in some big database of the born-in relations. We have lots of born-in relations. Edwin Hubble, born in Marshfield. Albert Einstein, born in Ulm. We find sentences in some large corpus, let's say we're using the web, that have both entities. So here's a bunch of sentences we might find. Hubble was born in Marshfield. Einstein, born 1879, Ulm. Hubble's birthplace in Marshfield, and so on. Lots of sentences. And now, from all of those sentences, for all those different entities, we extract frequent features. So we might parse the sentences. We might just use the words in between. We might have some named entities. We might have parts of speech tags, all sorts of things. We extract lots and lots of features. And now we take all those features and do exactly what we did for supervised classification. We have a ton of features and we have a large training set. And now we just train a supervised classifier. We'll need, like any supervised classifier, we need examples in the training set of positive and negative instances. We extract our positive instances from what we've seen in the database. So a particular person, Albert Einstein, being born in Ulm, is a positive instance. So from our supervised classifier, we can get a probability of the born-in relation for a particular data point, and now but we can condition that on all sorts of features we can extract from each sentence. So a huge number of features. Most recently, there's been a number of algorithms for doing unsupervised relation extraction, often called open information extraction, where the goal is to extract relations from the web with no training data and no list of relations. We just go to the web and pull information out. And here's the Banco et al. Algorithm, called the text runner algorithm. They first use parse data to train a classifier to decide if a particular relation, a particular tuple, is trustworthy or not. And so they have a small amount of parse data where they can use very expensive parse features to decide that a subject and a verb and an object are likely to be in a relation. Train a classifier that can do that for any relation. And now they walk through the very large corpus, let's say it's the web, in a single pass, and they just extract any relation between NPs, and we keep them if the trustworthy classifier says this is likely to be a relation between the two entities. And then we rank these relations based on redundancy. If we see a relation occurring a lot of times between two entities on different websites, then we guess this is a real relation. And this open information extraction algorithm extracts relations like FCI specializes in software development, or Tesla invented coil transformer, and so on, where we can extract a virtually infinite number of possible relations between any entities. All we have to do is see them often enough times on the web. How do we evaluate the semi-supervised and the unsupervised relation extraction algorithms? So since all of these are extracting totally new relations from the web or from some large corpus, there's no gold set of correct instances. We can't pre-label the web with all the relations that are on it. If we could do that, we'd be done. And that means that we can't compute precision because we don't know which of the new relations we've extracted are correct. And we can't compute recall because we don't know which ones we missed. So what do? We can compute an approximate precision, and we do this by drawing a random sample of relations from the output of the system, and we just check the precision of those manually. So we take some random sample, we pull out some the relations in that sample, and we measure how many of those were correct. And that will tell us an estimate of the precision of the system. And we can also do that at different levels of recall. So we could take let's say our relations are ranked, and we got a probability, there's probably a ranking. We could take the top 1,000 by that ranking, compute the precision for some sample of 100 of those, or take the top 10,000, compute the precision for some sample of 100 of those, and so on, and get the precision at different levels of recall. So in each case, we're taking a random sample. But there's no way to evaluate the actual recall, the complete recall of the system, without labeling the entire database, which of course we can't do. So semi-supervised and unsupervised algorithms for named entity extraction are two of the most exciting areas in modern research in extracting relations. And in general, the use of rules with named entities to extract relations, the use of supervised machine learning, and these new unsupervised approaches are all ways to solve the very important task of relation extraction, one of the core parts of information extraction.